Imagine, if you will, a star far grander than our own sun. For millions of years, it has burned with a brilliant, unwavering light. A colossal furnace in the silent expanse of the cosmos. It has forged elements in its core, transmuting simple hydrogen into the very stuff of life. But all things, even the most magnificent stars, must come to an end. Its fuel begins to wane, its internal balance falters. A cataclysm of unimaginable scale is set in motion. This star, once a beacon of stability, prepares for its final, breathtaking act. A supernova explosion that will briefly outshine its entire galaxy. This final, violent outburst is one of the most spectacular events in the universe. In a flash of cosmic brilliance, the star sheds its outer layers, casting them out into space as an expanding cloud of incandescent gas and dust. This beautiful, ethereal nebula will one day become the birthplace of new stars and new worlds, seeding the cosmos with the building blocks of everything we know. But what becomes of the star's heart? What is left behind after the cosmic fireworks have faded into the quiet hum of spacetime? It is here, in the aftermath of this stellar death, that we find the universe's most enigmatic creations. From the ashes of this cosmic titan, one of two extraordinary objects can be born. They are not stars, not planets, but something else entirely, the ghostly remnants of a once mighty giant. They are the universe's ultimate expressions of density and gravity. One is a neutron star, a city-sized sphere of matter so compressed that it defies our everyday understanding of physics. The other is a black hole, a region of space-time so warped that nothing, not even light itself, can escape its grasp. Both are born from the same violent death, yet they represent two vastly different and equally mysterious final chapters in a star's life. These celestial phantoms are more than just cosmic curiosities. They are laboratories for the most extreme physics imaginable. The journey to becoming a neutron star or a black hole begins with the same event: the collapse of a massive star's core. When a star at least 8 times the mass of our sun runs out of nuclear fuel, gravity, the universe's ever-present sculptor takes over. Without the outward pressure from fusion, the star's immense weight comes crashing down. The core implodes in a fraction of a second, collapsing under its own colossal gravity. The collapse triggers a supernova that blasts the outer layers into the cosmos. The star's fate is decided by one crucial factor: mass. If the star was massive but not overwhelmingly so, between 8 and 20 times our sun, the core crushes into unbelievable density. Gravity overcomes forces holding atoms apart. Electrons squeeze into protons, creating a sea of neutrons packed impossibly tight. The result? A neutron star, a sphere of pure neutron matter. But if the star was even more massive, over 20 solar masses, gravity is too powerful to stop. Nothing can halt the collapse. The core crushes inward past neutron star densities, shrinking smaller and smaller. It compresses into an infinitely small point, a singularity. Its gravity tears space-time, creating a one-way door with no return. This is the birth of a black hole. So the life of a massive star ends at a cosmic fork. Both paths lead to extreme gravity, but very different destinations. One path, the neutron star; the other path, the black hole. To truly appreciate the difference between a neutron star and a black hole, we must journey into a realm of physics that borders on the fantastical. A neutron star is a masterpiece of compression. Imagine taking a mountain or something far heavier, 1.5 times the mass of our sun, and crushing it down until it fits into a sphere no wider than a city, about 20 kilometers across. The result? A neutron star. A single teaspoon of its material would weigh billions of tons on Earth, more than all of humanity combined. Matter pushed to its absolute physical limit. That density gives a neutron star a solid exotic surface, a tangible celestial body with a defined structure, a crust of crystalline iron, and a core that may hold strange, theorized forms of matter. Its gravity is immense, thousands of billions of times Earth's, yet it's still an object governed by physics we can grasp. It spins at incredible speeds, sometimes hundreds of times per second, a dizzying cosmic lighthouse, the densest observable object in the cosmos. A black hole, however, isn't an object in the usual sense. It is a destination. At its heart, the singularity, a point of infinite density where our laws of physics break down. We can't describe the singularity, only what it does. The endpoint of gravitational collapse, surrounded by the event horizon, the point of no return. The profound difference between these two cosmic titans is most beautifully illustrated by how they interact with light. Gravity, as Einstein showed us, bends the fabric of space-time. Massive objects create dips in this fabric, and light, like a marble rolling across a curved surface, must follow these contours. Near a neutron star, this effect is dramatic. The star's immense gravity creates a deep well in space-time, and any light passing nearby is visibly bent around it. Gravitational lensing can make background stars appear distorted, can make background stars appear in different positions. Light can still escape a neutron star. If you were to shine a torch from its surface, an impossible thought experiment, that light would travel outwards. It must fight the star's colossal gravity, losing energy, becoming redder, gravitational redshift, but it would escape. The neutron star is still part of the visible universe. It exists within space-time, warping it significantly, but not breaking it. Its powerful magnetic fields can channel particles, creating beams of light we can see. A black hole's relationship with light is far more absolute and mysterious. The event horizon is the critical threshold. Any light ray that crosses that boundary is trapped forever. Not that light is destroyed. Space-time inside is curved so steeply that all paths lead inward to the singularity. The future of anything crossing the horizon is to move toward the center. No amount of speed or energy can overcome that warping. Given their extreme nature, how do we even know these cosmic phantoms exist? We cannot visit them, and in the case of black holes, we cannot even see them. Yet, we have found ingenious ways to listen for their whispers across the vastness of space. Neutron stars often reveal themselves through their incredible rotation. Many are pulsars, spinning rapidly and emitting powerful beams from their magnetic poles. These beams sweep across space like a lighthouse. If Earth lies in the path, radio telescopes detect a precise, rhythmic pulse. That clockwork signal was once nicknamed LGM-1. By studying pulses, we can measure the neutron star's mass, its spin rate, and test general relativity, watching gravity warp spacetime. Black holes require indirect detection. We look for their gravitational influence. Sometimes we find a star orbiting nothing, or a star wobbling as if dancing with an unseen partner. Measuring that orbit reveals the companion's mass. If too massive for a neutron star, we infer a black hole. We also see matter being pulled in. Gas and dust spiral inward, forming a superheated accretion disk that glows brightly in X-rays. A final scream before disappearing beyond the event horizon. Both neutron stars and black holes are therefore cosmic laboratories, helping us to probe the universe's deepest secrets. Neutron stars let us study ultra-high-pressure matter. Black holes push our understanding of gravity, space, and time. They are fundamental to our quest to understand the cosmos, beautiful, mysterious, and awe-inspiring final states of massive stars, silent monuments to a universe that is far stranger and more wonderful than we could ever have imagined.